In this video, I'm going to work through some practice problems where I evaluate line integrals computing flux of a vector field across a curve. So in this first example, we're given the vector field y comma 2x, and we're given a parameterization for a curve. So our integral is going to be the integral over c of f dot capital N ds. But as we learned, we're not going to actually compute capital N. What we're going to use is lowercase n, which is the vector that is y prime comma negative x prime. So important terminology here when we talk about vector fields and parameterizations, because we have two vectors that both have functions in them. So typically the way that we would describe this is we call the components of our vector field p and q, and we call the components of our parameterization x and y. So when I say y prime comma negative x prime, what I mean is the derivative of the y component of my parameterization, which in this case would be 3t squared, and then the minus derivative of the x component, which would be negative 2t. So this is going to be the integral. My parameterization goes from 0 to 2, so my integral is going to go from 0 to 2. This is going to be a dt integral, and it's going to be a dot product of two vectors. One of those vectors is little n, which we just figured out is 3t squared comma negative 2t. And the other vector is f, but it's f with the parameterization plugged in. So it's f of r of t. So in the capital F vector field, when I see y in the x component, what that means is the y component of the parameterization. So in this case, that's t cubed. So I don't want to write the letter y there. I want to write what y is on this curve, which is t cubed. And in the y component, my q of my vector field is 2x, so it's going to be 2 times the x component of my parameterization, so 2t squared. So what's this going to turn into? So 0 to 2, I'm going to compute that dot product. It's going to be t cubed times 3t squared plus 2t squared times negative 2t. That's going to work out to be 3t to the 5th minus 4t to the 3rd. And now that's just a regular Calc 1 style integral. I take the antiderivative of 3t to the 5th, that's going to give me 1/2 t to the 6th, and then the antiderivative of 4t cubed is t to the 4th. I'm going to plug in 0 and 2 and subtract, so I'll get 1/2 times 2 to the 6th minus 2 to the 4th minus 1/2 times 0 to the 6th minus 0 to the 4th, and that works out to be 16. So this is a similar problem, but this time we're given a curve, but we're not explicitly given a parameterization of that curve. So first we're going to have to find our r of t, our parameterization of this curve, and then we're going to set up our line integral like we did in the previous problem. So in this case, our curve is the graph of a function from a point to another point. And typically the way that we parameterize that is we let r of t be the vector where the x component is t, and the y component is the function of t, which in this case is square root of t. And so then little n, which is y prime comma negative x prime, that's going to be the derivative of the y component. That'll be 1/2 times t to the minus 1/2. And then minus the derivative of the x component, which will be negative 1. So my integral of c f dot n ds, right? That's the format for a flux integral. That's going to be the integral from, well, my parameterization has t in the x component. My curve goes from 0, 0 to 9, 3. So t is going from 0 to 9. My function is going to be 2xy, so that's 2 times t times square root of t. Remember that this is what we call x, and this is what we call y. And then x squared minus y squared, that'll be t squared minus square root of t squared, which is negative t. And then we get 1/2 t to the minus 1/2, comma, negative 1. So now we have to compute that dot product and then evaluate this integral. So 0 to 9, we get 2t squared root of t times 1/2 t to the minus 1/2 plus t squared minus t multiplied by negative 1. Now, when we multiply square root of t times t to the minus 1/2, those will cancel out. 2 times 1/2, those will cancel out. So we just get t. And then multiplying t squared minus t by negative 1 is going to give us minus t squared plus t. So this is going to be the integral from 0 to 9 of negative t squared plus 2t. we'll take our antiderivative, negative 1/3 t cubed plus t squared, plug in 9, plug in 0, and subtract. So that'll be negative 1/3 times 9 cubed plus 9 squared minus negative 1/3 times 0 cubed plus 0 squared. And that works out to be negative 162. All right, one last problem for this video. Again, we're not explicitly given a parameterization for this curve, but we're also not given an explicit function for this curve. But the curve here is part of the unit circle. The unit circle is a common curve that we see a lot, and we have sort of a normal parameterization that we use for that, which is cosine of t, comma, the sine of t. That's going to parameterize our circle counterclockwise, which we want, so that checks out. And we want the upper half of that unit circle, so it's not too hard to figure out that that's going to mean that our t has to go from 0 to pi. That'll give us that upper half circle. So little n, which as usual for flux integrals, is y prime, comma, negative x prime. So that'll be the derivative of the y component. Derivative of sine of t is cosine of t. And then minus the derivative of the x component. The derivative of cosine t is minus sine t. So minus sine t is just sine of t. So our integral over c of f dot n dx, our flux integral, is going to be the integral from 0 to pi, because our parameterization goes from 0 to pi. Our function f is x minus y, and again, when we look at our parameterization, the components of the parameterization, that's what we think of when we think of x and y. So x minus y is going to be cosine t minus sine t, comma, negative x, so that's going to be negative cosine t. And then we're going to dot that with the n vector, which is cosine t, comma, sine t. 0 to pi, we work out this dot product, so we're going to get cosine squared of t minus sine t times cosine t. And then we have cosine t times sine t with a negative sign, so minus cosine t sine t. And now we have to do that integral. So sine t times cosine t times sine t, those are all the same thing. So we get cosine squared t minus 2 sine t cosine t. Now, a couple things we have to do here to make this work. Cosine squared of t, we're going to have to rewrite using a half angle formula. So that's going to be 1/2 times 1 plus cosine 2t. So whenever we have an even power of sine or cosine, that's how we approach that one. And the 2 sine t cosine t, we can actually do that with a substitution. So we're going to let u equal sine t, and then du will be cosine t. So let's do all that. So we're going to rewrite this one more time, and then we'll go and do the antiderivative. So we get 1/2 times 1 plus cosine 2t, and then 2 sine t cosine t. So my antiderivative, the antiderivative of 1/2 times 1, that's going to be 1/2 times t. The antiderivative of 1/2 times cosine 2t, that's going to work out to be 1/4 sine of 2t. And then the antiderivative of 2 sine t cosine t, remember with my substitution, that's going to be 2u du. So that's going to be u squared. And my u was sine t, so that's going to be minus sine squared of t. And then I have to plug in 0 and pi and subtract. So I'm going to get 1/2 times pi plus 1/4 times the sine of 2 pi minus the sine squared of pi minus 1/2 times 0 plus 1/4 times the sine of 2 times 0 minus the sine squared of 0. But now sine of 2 pi, that's 0. Sine of pi, that's 0. Sine of 0 is 0. Sine of 0 is 0. 1/2 times 0 is 0. So all of that stuff is 0 except for the pi over 2. So pi over 2 is my flux calculation for this one. So the way you want to approach these flux integrals is to find a parameterization if it's not provided for you, figure out the vector little n, which is y prime, comma, negative x prime, plug the parameterization into your vector field. So you get f and little n, f with the parameterization plugged in, and n. You take the dot product and then you integrate with respect to t. So I hope these examples have helped. Keep working on it. You can do it.